Okay, so let's look at how this is implemented. There's an example. There's a Matlab example here. This is in the lecture folder. So what we've done here is created a function. So this function is returning the view factor f, and we'll call this function MC for Monte Carlo. It needs to take in some arguments. We have for this problem, the number of rays that we're going to trace, some geometry parameters. So this is that width of the base, the z position, and then the length, I think. So the length of the base. So we pass in all this stuff, and what we're doing now here is we're going to initialize these counters. So you initialize the counter to 0 so that you're just going through and incrementing when things happen. And then we go through this loop while the counter is less than our specified number of rays that we're going to emit. We do this process that we just talked about. So first, we randomly select array origin. So in Matlab, that's going to be, I need my x coordinate, I need my y coordinate. Rand is the uniform random distribution. So it'll call that rand, is basically a function. We'll return a random number between 0 and 1. And then we're getting our coordinate based on multiplying the length of the base. Okay, so we get x0, y0, that's the emitting position. And then we need to do our sampled ray direction. So again, we're doing full 360 degrees, multiply uniform random by the full 360. And then in the theta, the deviation from vertical, we have to do that correction. So that was arcsine of the square root of the random number. This will give us a nice uniform hemisphere around the emitting ray. Okay, so then we go through and solve for L here for this problem. Right? This is again for this example problem, solving for L. If your geometry is different, you're going to have a different equation there. We have our L, and then we go through and calculate the intersection points for X and Z based on the angles. Okay, and then we have to do all those criteria. So here's the criteria that we talked about. It's written a little bit like verbosely, I would say. So we have all these else ifs. There's a reason, again, for this. You're doing this thing 10 million times. You want the programming structure to be really efficient. So if I were to say, if L is less than 0 and, in the same line, and xi is less than, do that full thing in one statement, it evaluates every single comparison every single time. If we do it this way, it'll get to that first one and say, is L less than 0? Okay, maybe it is less than 0. So once in a while, it's going to come in here and say, yeah, hit 0, and then it skips the rest of those comparisons. You're significantly improving your computation efficiency if you just kind of think a little bit about the computer has to do this stuff, right? It has to evaluate all the things I'm telling it to evaluate. Okay, so we go through, we have our criteria, should be exactly what we talked about for this problem. If all these things, if any of these things happen, then it's not a hit. If none of them happen, then it is a hit. And then we come down here and we'll say, yeah, was it a hit? If it was, let's add 1 to our hits. If it wasn't, we're adding 0. And then we just go through that whole process until we hit our ray count limit. And then we report back F, which is hits over the number that we emitted. Any questions on this? Okay. So we can run this. Let's see. Here I have a program set up with A is 1, B1, B2, C is 2. And this is our function call. So it's going to just print out the value. Before we do this, let's look at the ease equivalent. So in ease, here's the same thing. In ease, the function, we can go in here, radiation view factors, 3-dimensional, and look for F3D10. So this is exactly the same one that we're doing. So we'll call that one just to see. And we do that and we get what, 0.1403. So this is the analytically expressed solution. It's deterministic. We run this every single time. It's going to give us the same answer. Now let's go back here and let's pick, I don't know, right now I've got 1 million. Why don't we start running it with, let's start running it with 1,000 rays. So I'm going to run this. Everything else is commented out. So I run it And I'm getting down here, my view factor is 0.132. Okay, well, that's a little off, right? It was 0.14, 0.13, but let's try it again. So run it again. 133, 132, 123, right? So 146. So you can see like you're getting quite a lot of variation, right? So that tells me maybe I don't have enough rays. So I'm going to increase the number of rays I'm sending here. Let's maybe make that 1,000,000 rays. So now I'm doing this computation 1,000,000 times, and I get 0.1403. It's still not going to be perfect, but the variation is going to be a lot smaller. One thing you do want to do with this is you need to kind of prove, at least to yourself, that your problem has converged. So one way to do that is we're going to go through, let's just run this little code here. What this code here is doing is we're going to take NV as our number of rays. So NV is the number of rays. I'm going to test the number of rays, 10, 20, 30, and so on, all the way up to a pretty big number. And what I'm going to do is for each of these ray counts, I'm going to run the simulation 25 times and then keep track of what's the average of all those runs. And then what's the standard deviation of all those runs? So we can get a sense of how good is it at estimating the average value, but also what's the uncertainty in the model. So if we do this, maybe take a second. Okay, no, went pretty fast. So we do that, and then we can look over here. So let's see, F bar. So F bar for each of these, 10 rays, not very good, right? 0.15. But as you go on, you start to see, they're getting really close to the true value. And you can look at the standard deviation, and you'll see 0.1 standard deviation on a view factor of 0.14 is not very good, right? It's hard to see that, but this is 0.1. As you go further down, of course, it gets smaller and smaller, more rays. We can look at let's see, I think we had this plotted in ease as well. So I just took this data, plugged it into ease in a lookup table, and I'm plotting this. And you can see, as a function of the number of rays, the estimated value with the red square, and then the uncertainty on that estimated value. So I don't know if I was making a judgment on this, I would say, if I don't care about my view factor, say within a percent or two, 100,000 rays is certainly adequate for that, probably 10,000. And this program runs quickly enough. It's hard to imagine why you wouldn't want to do more rays, but you do get into situations like this one where it's pretty expensive. It can take a while to run this, as some people know in here. Okay, so any questions on that, or good? One last thing that I want to talk about for you guys to give you some information on your homework, which will be posted. These that we've talked about are really simple shapes, right? What do you do if you have a complex shape? Not just for the hit or the target, but also for maybe the emitting surface. So let's take this example where here's my coordinate system. Y. This is X. Let's say I have some complex shape that's not really easy to sample, right? It's not easy to take a random number and sample in some coordinate system. So let's see how well I can draw the hexagon. So this. Okay. So I have this surface. I'm emitting from this surface. How do I tell, or how do I get a uniform sampling from this surface? Right? I can't write an equation. Okay, this is some linear function and sample. It's not really straightforward how I would do this. Maybe some of you can guess though. What you'd want to do is, like we do for the target when we do this hit testing, you can do hit testing on the emitting surface as well. So let's create a bounding box. This bounding box here that just encompasses all the edges. Right? just encompasses all the edges of whatever complex shape we have. Now, if I want to sample from this, I can say, all right, my first step is now a little different. I'm not just randomly sampling from within this region, I'm sampling from the bounding box. And then I sample in the bounding box, I have to determine whether the ray is within the emitting geometry, and then I can use it, right? So my first sample might be here. I do a hit test for this complex shape. It's in there, great, I'll use this ray. Next one's out here, it's not in there, so I'm not going to use that ray. So now the whole, the process will just continue. I got a uniform sampling over the entire bounding box. And this guarantees then that I have a uniform or representative sampling within the emitting surface as well. So the view factor for this is still going to be the number of hits on the target divided by the number of rays from the emitting surface. Right, and the number of rays from the emitting surface are only these rays, okay, only these rays that fall inside this hit test region. Okay, so that's one way to handle complex shapes. What I'm going to do on the homework is I have a function that will help you evaluate for any polygon, convex or not, whether a ray exists within that polygon. So I'll give you that function, and then it'll be your job to implement that in a ray tracing program. Okay? It'll be really fun. Any questions? Yeah. That's right. So this method is easiest to implement in 2D surfaces. If you have a 3D surface, typically how you deal with that is either the surface has to be analytically defined, where you can define the surface using an expression and then test it that way. Otherwise, you discretize it into a bunch of little elements that are flat. Okay. Okay, that's all I have for today. Thanks, everyone.